Welcome back. In this session, we are going to show that the set of all real-valued continuous differentiable or integrable functions defined on a closed interval AB is a real vector space with the usual addition and scalar multiplication defined on this set F over the field F. And for this case, this field is simply the field of real numbers. Okay, so to prove this one, we have to show that all the 10 axioms of vector space are satisfied by this set, capital F. So proof. Let F, G, and H be functions in this set, and let alpha, beta be in the field F, and for this case, the field is just a set of real numbers. Then plus and this multiplication is addition and scalar multiplication. Respectively on this set. So the first property to prove is closure with respect to addition on the field on the set capital F. So property one, closure. So let's see whether closure with respect to addition is satisfied on this set F. So F and G are two functions in this set F. Then if we take F, we add to G, these being functions of X. So we write this sum as F of X plus G of X. This by definition. And since sum of two functions, remember this for all X in this closed interval AB. So since the sum of two continuous functions is also continuous, then F of X plus G of X must be in the set F. That is to say, closure with respect to addition holds on this set F. So that's first property done. Property two, let's test for commutativity. Does commutativity property hold? So we have two functions F and G, which are in this set of continuous functions on the closed interval AB. Then F plus G, well, these are functions of X. The sum is written as F of X plus G of X. And then this can be written as G of X plus F of X. And the reason is because by commutativity, of addition on the field F, we get this field of real numbers. So that's why we are able to change f of x plus g of x to g of x plus f of x. And then if f plus g of x was f of x plus g of x, then to get these results here, we must have had f plus g and then of x. And don't forget that this is f plus g of x. So i.e. from this one, we can say that f plus g is nothing but g plus f. Therefore, commutativity with respect to addition holds on this set F. Number 3, we prove associativity with respect to addition. Does associativity property hold on F? Now we pick 3 functions. We have specified f, g, and h are functions in this set F. Then f plus g plus h of x will be f plus g of x plus h of x. This is by definition of doing this sum. And then this other part is the same as f of x plus g of x, and then plus h of x. But then, because these are real numbers, so remember this for all x, the closed interval AB, we can switch the places for brackets and then say f of x plus g of x plus h of x for this plus, and this is because by associativity of addition on the field F, just remember the field of real numbers. So the next step from here, if this result was from here, then this must be the result from f of x plus g plus h of x. I remember we came from f plus g and then plus h of x. So from the right hand side in this step, we can easily see that f plus g plus h of x is f plus g plus h, and then I put of x outside. Now, what does this one tell us? This implies that if I take f plus g, I add to h, is the same result as taking f plus g plus h. And you see this is the associative property that you're trying to prove. So therefore, associativity with respect to addition holds on this set capital F. Next, property 4, additive identity. Additive identity. Does additive identity exist? We say, let us have f to be a function in this set f. Then it implies that also its negative is in this. Okay, that's not negative, so additive identity. So let f be a function in that set f. And let's define a function be 0 for all x given in the interval AB. Then f plus this 0 function will be f of x plus this 0 function, which is the same as writing f of x plus 0, because I've defined this one to have value of 0 throughout for all values of x in the closed interval AB. And this is f of x since f of x and 0 are in F. And we know when we add any real number to 0, we get the same real number. So i.e. f plus 0 is the same as f. Therefore, additive identity exists on this set F. Number 5, additive inverse. Does additive inverse exist? So let f of x be a function in this set. Then there exists a function negative f of x also in this set. Such that if I pick f of x plus minus f of x, then I'll have f of x minus f of x, and this will give me 0, or this difference of two same functions. Therefore, additive inverse exists on this set F. Now, the next thing is to prove closure with respect to multiplication, closure with respect to scalar multiplication, does this property hold? Now let alpha be in the field F, the same as the set of real numbers. And then we have the function F in the closed interval AB. Then alpha F of X is an element in this set F, because we are simply multiplying the function by a scalar. So the scalar from F when you multiply by the function, then you still get another continuous function within the same set in the interval AB. Number 7, distributive property. Now, if I have alpha into F plus G, then it's the same thing as alpha into F of X plus G of X, which is the same as alpha F of X plus alpha G of X. What is allowing me to do this one is by distributivity of multiplication over addition on this field F, they're the same as the set of real numbers. So from this one, alpha F plus G of X, now this is the same thing as saying alpha F plus alpha G and then of X. So this means alpha into F plus G is nothing but alpha F plus alpha G. And actually this is what you wanted to prove. So distributivity hold. This set of continuous functions. Number 8, still distributivity, but then write distributivity. So if I have alpha plus beta, I multiply by F of X. Remember, we had defined alpha and beta to be elements in the field F, and F is a function in the closed interval AB. So this will be the same as take alpha multiplied by F of X plus take beta multiplied by f of x. So we'll have alpha plus beta f of x is equals to alpha f plus beta f, and then you write here of x. So this means alpha plus beta, when you multiply by f, is the same thing as alpha f plus beta f. This is what you have to prove. So therefore, distributivity property also holds. Number 9, associative with respect to scalar multiplication. Now we have alpha, beta being elements picked from the field F. Then if you pick a function in this set, then you say alpha beta times f of x is the same thing as saying alpha, and then f of x is a function within interval AB. So you can write this as beta f of x, and then this can be written as alpha into, actually I need to put the bracket here. So I do the multiplication of beta by f first before multiply by alpha. So now this is the same as this. What's allowing me to do this is because of associativity of multiplication on the field F of real numbers. That's why I'm able to change the location of the brackets from this point to this point here. i.e., this is the same thing as saying alpha beta times f is the same as alpha beta times f. And this is the associativity that we wanted to prove. So therefore, associativity holds. And then lastly, remember this for all x in the closed interval AB. Now scalar multiplication by 1. So 10 identity multiplication. So we have an element 1 in the field F. So just same as real number. And then let's have a function f from this set, capital F. Then if you take 1 times f of x, it's the same thing as saying 1 times f of x, and 1 times f is just f. So this is what we have. And so this implies 1 times f is just f. So identity multiplication is also possible in the set F. Therefore, identity multiplication is defined on this set F. I remember here, this for all x values picked in the closed interval AB, and we are moving from here to here because of multiplication of unity by F. So we multiply or multiplication of unity in the field F, so that now 1 multiplied by any number gives you that same number. So since all the 10 axioms of a vector space are satisfied, then the set of all continuous differentiable and integrable functions in the closed interval AB is a vector space. That's how we solve that.